Multivariable Calculus, Section 13.3, Area and Volume by Double Integrals. Now, remember, we're going to review volume above simple regions that we talked a little bit about in the previous section. This region is called vertically simple because we can always move from the bottom curve to the top curve vertically. And so for our integral, we integrate with respect to y first between those two curves, and then we integrate along the x-axis from a to b, and that will get us the entire volume beneath the function f of xy. This region is called horizontally simple because we can move from curve to curve, from left to right, always across the region. And so first we integrate with respect to x, moving from curve to curve, and then we integrate along the y-axis from c to d. Now, if the function value, the z value, is always greater than or equal to 0, then we're going to get volume. If it varies, then anything below the xy plane will be returned by the integral as a negative value. So let's talk about area of simple regions. How does the area relate to a double integral? Well, here's our double integral for the volume under a positive function given a certain region of the xy plane. Now, the function is your z value. That's your varying height of the solid. So here's a region. Now, what if we let the function value be 1? In other words, z is always 1 unit higher than the xy plane. Well, then our solid volume is going to have the same numerical value as the area of the region. So now we get volume equal area of region if we let our z value always be 1. Here's an area example. Use a double integral to find the area between y equal x and y equal x squared minus 2x. Well, of course, I always like a picture. So here's our two functions in the xy plane. There's the region that we're trying to find the area of. And we could do this with single variable calculus, but now we're learning a new method. So this is vertically simple because we can always move from the blue curve to the red curve vertically. We wouldn't be able to do that horizontally. So here's our integral. We're going to integrate with respect to y first. And we're going to make our z value 1 so that the volume is numerically equivalent to the area. And we need to know our intersection points. So we set the two functions equal, move x to the other side, factor, and pretty obviously we're going to be integrating from 0 to 3 along the x-axis. And then our function values, we're going to go from the bottom function, which is the parabola, up to the linear function, which is just x. So now the antiderivative of 1 with respect to y is just y, and so we're going to evaluate that antiderivative with the two functions that were the limits of integration. So we just subtract x minus the quantity x squared minus 2x, and we get 3x minus x squared. And now we have a simple integral, which we find the antiderivative of, and then evaluate from 0 to 3. And we end up with the area being 9/2, which would also be the volume if the z value is always 1. Okay, now we're going to talk about the volume between two surfaces. Something like this. How would you find the volume between the two surfaces, the blue one and the pink one? We have a z value for the top surface. We'll call that function sub 1. And we have a z value for the bottom surface. We'll call that z sub 2 or f sub 2. And so all we have to do then is take the volume under the top function minus the volume under the bottom function. So pretty simple to do. So let's look at some problems. Number 10, use double integrals to find the area of the region in the xy plane bounded by y equal x squared and y equal 2 over 1 plus x squared. So I like to take a look at the region we're integrating above. So the red curve is the x squared and the blue curve is the rational function. And the area of the region is shown in green. So we're going to be wanting the area of that, and so using double integral, we're going to pretend it's volume, and we notice that we can move vertically but not horizontally. So we're going to have to integrate with respect to y first. It's vertically simple. So this is the integral we're going to use, and we are going to replace the function with just 1 so that the heights are all 1. That'll make the volume the same as the area. So we need to know what a and b are along the x-axis, so we set our two functions equal, cross multiply, bring the 2 over, and that will factor. And x squared plus 2 doesn't yield any solutions, so x is going to be 1 and negative 1. So a and b are going to be 1 and negative 1, and we're going to integrate 1 with respect to y and get y, and also plug in the limits of integration. So we'll integrate that, and we get 2 arc tan x minus 1/3 x cubed from negative 1 to 1. Plugging in our values, we get pi over 2 minus 1/3 for x equal 1, and negative pi over 2 plus 1/3 for x equal negative 1, which simplifies to pi minus 2/3. Number 14, find the volume below z equal 3 plus cosine x plus cosine y, but above the region of the xy plane bounded by x equals 0, x equal pi, y equals 0, and y equal pi. So this is a rectangular region, and so we don't have to worry about which way we're going to integrate first. It's vertically and horizontally simple. So just arbitrarily, I chose to integrate with respect to x first. And so the antiderivative of 3 is 3x, the antiderivative of cosine x is sine x, and in the last term we treat cosine y as a constant, and so it's just that times x. And then we put pi and 0 in for the x values and subtract, and we get 3 pi, and then sine x is 0 at pi, and then we get pi cosine y. And then when we plug 0 in for x, all three terms are 0, so it would just be minus 0. Now we integrate with respect to y, and we get 3 pi y, and then the antiderivative of cosine y is sine y, and again we evaluate at pi and 0, and we get 3 pi squared plus 0 for the first limit of integration, and then everything's 0 when we plug 0 in. So there's our final answer. Number 22, find the volume below z equals 1 plus x squared plus y squared and above the region of the xy plane bounded by y equal x and y equal to minus x squared. Okay, so let's take a look at the region in the xy plane that our volume is lying above. And there it is. There's a line y equal x in red and the parabola 2 minus x squared in blue. And so the region we're talking about is that green region right there. Now we'll notice that it is vertically simple, but not horizontally simple, because horizontally, part of the top part, you would have to go from the blue graph to the blue graph, and that's a no-no. So we'll be integrating with respect to y first. So there's our integral, and we're integrating with respect to y first, so it's dy dx, and the limits of integration for y are from the line, the red line, up to the parabola, so that's from x up to 2 minus x squared. But what about the limits for x? Well, we're going to need to find the intersection points. So we set x equal to 2 minus x squared, and solving, we get two intersection points, 1 and negative 2. So the x limits of integration are going to be negative 2 to 1. And when we integrate with respect to y, our integrand becomes 1 goes to y, x squared is treated as a constant, so we get x squared y, and then we get 1/3 y cubed. But then we have to substitute 2 minus x squared for all the y's, and then subtract when we substitute x for all the y's. So here's what we get. Now, that, in order to integrate that by hand, we're going to have to multiply it out, and in order to integrate it on your calculator, you will have to type very, very carefully. So I went ahead and did it by hand, which is upsetting our little friend here because it's so huge. Now there's no room on this slide, so let's proceed to the next slide. And here we have the steps written out for you. You can pause the video and study this if you wish, or just move on. The answer is 837/20ths. Number 34, set up but do not evaluate an iterated integral, aka a double integral with x and y limits of integration, that gives the volume of the solid that lies inside the sphere x squared plus y squared plus z squared equals 2, but above the paraboloid z equals x squared plus y squared. Yes, the word iterated just means that you have figured out what the individual limits of integration are. You don't just have two integral signs followed by your integrand. So here's our sphere with radius √2, right? And here's our paraboloid, and they intersect somewhere. And so what we want is the volume that's above that red and below the green, so the little bubble there above the xy plane. And so the region is going to be the shadow of that red circle where the two curves, where the two surfaces intersect. And so we're going to have to figure out what that region is. So the first step then is to figure out what radius the red and therefore the purple circles are going to have. So we're going to take the equation of the sphere and notice that x squared plus y squared is equivalent to 2 minus z squared. So then we can combine that with the paraboloid, the fact that z equals x squared plus y squared. And so we can set z equal to 2 minus z squared and put everything to the left and solve, and we get some familiar numbers. The book really likes these numbers, but in this case z can't equal -2 because we're talking about a radius here. So z must be 1. And if z is 1, then that means that our purple circle's equation is x squared plus y squared equals 1. And now we want to take the integral of the top surface minus the bottom surface. Now it's arbitrary actually whether we integrate with respect to y or x first, because the circle, the purple circular region on the xy plane is both horizontally and vertically simple. So I just arbitrarily chose to integrate with respect to x first, which means that y is going to go from -1 to 1, and x is going to go from the left half of the circle to the right half of the circle, which if we solve, we get the square root of 1 minus y squared, the positive and negative square roots. So our integral is going to be -1 to 1, and then negative square root of 1 minus y squared to positive square root of 1 minus y squared. And then the top surface is your sphere. So if I solve for z using the sphere's equation, I get the square root of 2 minus x squared minus y squared for z. And then the bottom surface is the red one, the paraboloid, and that's already solved for z. And so the question said just to set it up, and we don't have to integrate it. It would be difficult to integrate this, I think. And so now I leave you with problems to do and a little bit of humor. This joke was stolen from the website Calculus Humor, which was started by Greg Tewksbury and Kaylin Willingham.